A Lewis structure is the drawing of the valence electron configuration of a molecule. A very simple example will be a bromine ion. Now, what's the valence electron configuration for this? Well, I have to think about what the valence electrons are of bromine. It has 7 valence electrons. And it has 1 additional electron because of the ion. And all I'm really doing is just drawing around the outside the electrons. Just like that. And this would be the Lewis structure for a bromine ion. And these are going to be important because it helps see the lone pairs. And the lone pairs are going to be important for the geometry of molecules, and in organic chemistry they'll be important for different types of reactions that take place. Things will be attracted to a lone pair because it has high electron density. So this is for something simple you can do for things that are bonded, like this. Oh man. So yeah, for something that's bonded like this, I do the same process. Count the valence electrons for every individual atom. So fluorine has 7 valence electrons, hydrogen has 1. I'm just going to draw them individually at first. So if they were separated, the Lewis structures would look like this. But they're bonded, so they're going to share a pair of electrons here. And this is normally just represented by a line. And in order for it to be a Lewis structure, then I need to draw the lone pairs, which it will have 3. So that's a Lewis structure for that. Something with some more bonds. Water. Oxygen has 176. And there are more than one hydrogen, so it's important to... Some people like to count up the total number of valence electrons. I don't really do that, but sometimes people will say, let me see, they'll say, well, there are 2 hydrogens, so there will be 2 valence electrons for a total of 8 valence electrons. And then they'll go ahead and say, well, oxygen needs, this is how I used to think of it. Now I don't even think about it because I've done so many of them. Oxygen needs 2 valence electrons. How am I going to share my total electrons in order to gain octets for everything? Hydrogen needs 1 electron in order to gain a helium configuration, so it's looking to share 1. So if I have 2 hydrogens, each one of them shares 1, then I'm going to have a total of 8 for oxygen and a total of 2 each for hydrogen. So here's the oxygen. It needs 2 additional electrons. If it shares 1 with 1 hydrogen and 1 with another hydrogen, then it will have an octet. And what people like to do with the counting of valence electrons is to make sure they got it correct. What they'll do is say 2, 4, 6, 8. I have 8 valence electrons, therefore I drew it right. If they added an extra bond or if it failed to include a bond, then it will show up they'll be missing some electrons. So that's a good way to check in the beginning. But as I say, once one has done just even a few of these become second nature and people don't even have to think about them anymore. And it's helpful in the beginning just to understand the idea of lone pairs, because lone pairs, the bonds are usually quite a bit more obvious than if something has a lone pair or not. You have to kind of stop and think about it in the beginning at least. Now that, well, at least now that I've done them so many times, I don't think about them at all. I already know they're there if they're there or they're not there. So let me do one final example. Carbon dioxide. And if one wants to do a total, then they can just... That's not 20, it's 2 oxygen. For a total of 16 electrons. So having a look at here, carbon needs 4 electrons. Needs 4 to gain an octet. Oxygen 2 to gain an octet. There are 2 oxygens, so I think I can see a rather convenient way of doing this sharing. If oxygen were to share 2 electrons with carbon, that would bring it up to 6, and then if the other oxygen were also to share 2 electrons with carbon, that would bring it up to 8, and then everything would have 8. So this is what this looks like. Carbon, it shares 2 electrons with an oxygen. That would give the remaining oxygen, or not the remaining oxygen, the remaining electrons would be 2 lone pairs. If I were to do the same thing, the other one, then the other oxygen would also have 8 electrons. 2, 4, 6, 8. 2, 4, 6, 8. So this has an octet, this has an octet, and carbon also has an octet. 2, 4, 6, 8. So that is also another good way of checking to see if the Lewis structure is drawn correctly. It's just to see if there are 8 carbon, or there are 8 electrons around each atom, unless it's a hydrogen, in which case there will need to be 2. But it's hard to mess that up because as soon as it bonds to something, it already has 2 electrons. Normally that's not the one. But there are also other circumstances where the Lewis structure is not predictable, but we don't really need, it's just not really that important right now. But really what's important, I think, out of the Lewis structure is just to be able to see lone pairs. And in the future, when we learn about the geometry of bonds, the lone pairs are going to become very, very important. And as I say, normally the bonds are very obvious, but in the beginning, the lone pairs, people aren't really so familiar with them because they just learned about them. So don't really worry about situations where something like boron. Boron is just a really weird element. It's electron deficient. Sometimes it'll form like weird bonds. I think this is right. And there'll be another boron, then I'll have like these it's like weird like curved bonds. I don't even remember what they are. It's just too weird. I remember seeing that in like an organic chemistry book somewhere. And it's an electron deficient or something like boron trifluoride, I think, is something. And its electron deficient boron has only 6 valence electrons here, 2, 4, 6. And there will be other situations where something with access to this d orbital right here. So something like, I don't know, like sulfur, it can get like 6 bonds or something to something really electronegative like chlorine or fluorine or something. And even noble gases, which people used to think couldn't even make bonds because they already have octets. can actually make bonds and get an expanded octet where it'll have like 12 electrons around it or something like that. But it's not really that common. Most of the time, we're going to be looking at stuff, at least in the beginning, we're going to be looking at stuff with like non-metals like carbon, nitrogen, oxygen, fluorine, stuff like that, and that kind of stuff isn't going to happen. But just know that it does exist, and it's just not really that important right now. I really wouldn't recommend spending any time on it as of right now. It's just they're just not all that common.